Okay, continuing our discussion of seismic slope stability analysis. In the previous video, we saw kind of an overview of how earthquakes can reduce your factor of safety, and we showed with the very simple pseudostatic analysis you can add a KW term, which represents an increase in the forces driving failure, and how you'd go about updating your calculations for the factor of safety. So now we're going to continue that, and we're going to incorporate that, but also expand it, and there's a methodology called a pseudostatic screening analysis, which is kind of a more comprehensive way in which you approach considering seismic issues as you analyze the stability of a slope. So this is a good method to screen sites that aren't expected to lose a large amount of strength during an earthquake. The more comprehensive method we talked about earlier would be what you do for the more extreme cases. But the way this works is you have 5 steps. You come up with a reference peak acceleration, an acceleration multiplier, that then is then used to calculate the pseudostatic coefficient K. And then we also apply a strength reduction factor, which we'll talk about. And then we consider what acceptable minimum factor of safety we need, and then we also look at our tolerable permanent deformation. So we're going to talk about each of these 5 components in more detail. First of all, we have to come up with a peak acceleration, which is typically expressed as some fraction of gravity, A ref over G. And this is typically either the peak bedrock acceleration, PGA rock, or the peak acceleration at the top of the slope, which we call PGA soil, and is determined from a dynamic response analysis. Fortunately, the United States Geologic Survey has a website where you can look up the peak bedrock acceleration for anywhere in the U.S., and you can analyze a number of different return periods. So the peak acceleration depends on what kind of event you're looking at. So the 2 that we most typically look at are the 10% probability of exceedance in 50 years, and then the 2% probability of exceedance in 50 years. So the 2%, it's going to be more rare. That's going to be a larger peak acceleration. So that's so again, you typically look at both of these, and then determine at some point along the way you have to determine what it is you're going to design for, and that's going to be a function of risk. How much it would cost to repair the slope, what are the consequences if the slope fails, etc. So the way this works is you can look this up on a map like this. This is the 10% probability of exceedance in 50 years. It's color coded. You can just kind of narrow in where you are and scale it off of a map if you like. Notice there's a very high risk area here in the east part of the United States. I think it's called the New Madrid Fault. I could be mistaken there. And of course, in the west we have the Rocky Mountains, and then a very seismically active section in California as well, and Seattle. And then there's a similar chart for the 2% probability of exceedance. You'll see it's the same colors, but according to the legend here, this is higher. So this tops at 0.8. The previous one is at 0.4. And so they're different values. Now, if this map, typically you'd probably want to drill down and get something a little more specific. And so if you use this link shown here or Google this, you can bring up the Unified Hazard Tool part of the USGS website. And the way this works is you enter a latitude and longitude, or you can click on this button and you can actually zoom in and click on a point on a map, or you can even enter an address and it will zoom in and find that, and then it will load the corresponding latitude and longitude. And then you also tell it whether you want peak ground acceleration or peak soil acceleration, and then you pick your return period. There are three: 2% in 50 years, 5% in 50 years, and 10% in 50 years. So you pick your return period. And so if you pick this choose location button, this is what comes up. You can you can just click on a map, or you can type in an address, and and that basically creates the point here that you want. You can also click here and just drag and drop this wherever you want, and then you click use this location, and it loads the latitude and longitude here. And then this button comes up and you click compute hazard curve, and then it displays this result. And in the lower right corner, this peak ground acceleration, so in this case it would be 0.6, basically 64% of gravity in the horizontal direction, so that would be a pretty serious earthquake. And you can click on alternate return periods and the plot will automatically refresh. So this is a really nice, convenient, simple to use system for finding peak ground acceleration in the United States. Once you have that, to get the seismic coefficient K that we use in the pseudostatic analysis, you take the peak acceleration that you found in the previous steps that we described, and then you apply an acceleration multiplier, which is a scaling factor, and we typically use 0.5, and that's discussed more in table 10.1. In your textbook, you'll see people have proposed different acceleration multipliers, all the way from 0.13 up to 0.75, but again 0.5 is kind of a mid-range acceleration multiplier. And together this gives you the seismic coefficient K that we then use in the pseudostatic analysis. So the next thing we do is a strength reduction factor. And McDeasy and Seed found that non-liquefiable soils undergo small strains under cyclic loads as long as they're loaded to less than 80% of their static strength. Therefore, most experts recommend that static strength should be reduced by 0.8 when performing a seismic analysis. And so we basically reduce our undrained strengths when we do our limit equilibrium analysis. So you've added the seismic coefficient K. That modifies the factor for the formula safety, but you also use a reduced shear strength. Okay, now in step 4, we take the factor safety that we've calculated using the seismic coefficient and the reduced shear strength, and then we decide what's our acceptable factor of safety for a seismic analysis. That ranges from 1 to 1.5. Again, you can look at table 10.1 in the textbook to see a suggested set of ranges. Now, you might think, boy, that's a really small factor of safety. Yes, but remember we're considering something that doesn't have a very large probability of happening. And we've also have some built-in factors of safety with some of the way in which we come up with the coefficients and reduce the strength. And so this is typically the range that a factor of safety that's suggested. And another thing you look at is if you look at the max, based on this process, you determine what the maximum displacement is expected, and that's based again on table 10.1 in the text, and it ranges from about 0.15 to 1 meter. Okay, what kind of shear strengths do we use? If you have a new slope and you're expecting an earthquake shortly after construction, you do a total stress analysis with unconsolidated undrained tests. If you have an existing slope and mean a natural slope, and it's a long time after it's come to equilibrium, then again we use a total stress analysis and unconsolidated undrained tests. And however, if we have a new slope, a constructed slope, but it's a long time after equilibrium, so we have an embankment or a dam or a levee, in this case we would use consolidated undrained strengths, and we could do a two-stage analysis, which is similar to rapid drawdown analysis or a simplified procedure. So the two-stage analysis, very similar to the three-stage one we talked about earlier. The first stage is based on static pre-earthquake conditions. We calculate the normal stress on the failure plane at the end of consolidation and the shear stress on the failure plane at the end of consolidation. And during the second stage, as was the case with rapid drawdown, the effective stresses from stage 1 are used to find the undrained shear strength tau FF using a very similar approach. And the factor of safety is computed using this tau FF and the loading conditions corresponding to the earthquake. In other words, with the kW force applied. So very similar to the rapid drawdown case. With a simplified procedure, we do this all in one step. The strengths are defined using what's called an R envelope. And so it's kind of a shortcut to a two-stage analysis. And the factor of safety is computed using the loading conditions corresponding to the earthquake or the kW force. And so another caveat is even though the strengths in the R envelope are undrained, we use pore pressures corresponding to pre-earthquake conditions so that we get the proper effective stresses are found and fed into the R envelope equation. So what is an R envelope? It's kind of a modified version of a Mohr Coulomb strength envelope, but it's a little bit different. So you take the effective stress on the failure plane, or the minor principal effective stress at the end of the consolidation stage, and then you add on the deviator stress at failure, and then you construct this circle and do this for different consolidation stresses, and you end up with a CR and a FR. And so it's a hybrid because we're combining an effective stress from the consolidation stage and a deviator stress from the failure point. So these happen at two different points in time. So why use this? What's the point? Well, the point is the final curve you get from this is very similar to the sigma prime FC versus tau FF curve, or tau FF versus sigma prime FC is what that should say, that we used in rapid drawdown, the D psi curve, but it's a little bit more conservative. If you look at figure 10.6 in the textbook, you'll see that the envelope from this is kind of just below that one. And so again, the sigma prime FC is the effective normal force on the failure plane at the end of consolidation. Tau FF is the resulting undrained shear strength, and so the R envelope is kind of a shortcut to get that. So that's why we do that. So it allows you to do that multi-step analysis more simply and directly, just in a single step. And so that concludes the discussion of the seismic screening analysis, and that's a recommended way of analyzing slopes undergoing seismic conditions.